All right, we're rolling. Welcome to Unit 3, Applications of Differentiation. This will be our first video. I'm trying to work on talking loud so that you can hear me. I know there's been some complaints with my sound thing. This is a link to the KUDs, which you can't get to, but I don't really want to at this point because we went over them in class already. So, the first thing in Applications of Differentiation is the extreme value theorem. Theorem. There it is. All right, so the extreme value theorem says this. If f, well, you can read this, I guess. If f is continuous on a closed interval from a to b, then f has a minimum and a maximum on that interval. Seems reasonable? So we get a continuous function from here to there, a to b. Someplace we could have a low part. Someplace we could have a high part. It's guaranteed. Okay? The extreme value theorem. Now let's prove it. No, we can't prove it. Okay, we're not going to prove things. We generally with theorems in calculus, they're called existence theorems, and there's that thing. And I'm going to just pause. I'm going to stop, and I'm going to say change the color scheme. But you know what? It doesn't really ever do the right thing. So we'll just get used to that popping up. Maybe I'll ask somebody. So these are existence theorems. That's what I was saying. They're existence theorems. They tell that the value exists, but they don't necessarily tell us how to find it or anything like that. So we're going to try to get into that. So there are several kinds of extrema that we want to worry about as we work through this. We have what are called absolute minimums and versus a relative or local minimum. We have absolute maximums, and then we have relative or local maximums. Okay? So the absolute minimum is the lowest low point. Okay, so the lowest low point on the interval, we call that the absolute minimum. The highest high point, you guessed it, it's the absolute maximum. Okay, the highest, it's not quite working out this morning, the highest high point, maybe I'm writing too fast, the highest high point. Okay, so if we look at this, my lowest low point looks to be about here, so that's my absolute minimum. Okay, abs min. My highest high point, if I was guessing, would be about there. And I'm going to call that my absolute max. Okay? We're talking about relative minimums and maximums. We're talking about basically the peaks and the valleys within my interval. Okay, the peaks and the valleys. So I've got a peak right here, ish. Okay, that's a relative or a local max. I'm going to call it a local. Okay, got a local max. Okay, here we've got a local min. Okay, here we have a local max. Here looks like I've got a local min, local or relative. Local is easier to spell, I guess. So, all right, so that's what's going on. So my absolute minimum could be also my local minimum. Doesn't have to be, though, as you can see here. My absolute maximum could be also a local maximum. Okay, in this case it is, but if for some reason this thing was extended up here, then my absolute maximum could be there. Okay, so they can be the same thing, they can be different. So when we're talking about these guys here, we're talking about peaks and valleys. That's what we're looking for, peaks and valleys, and it's a highly technical math term, but peaks and valleys, those are extrema. Okay, and the highest high point, the lowest low point. Ta-da! All right, so my extreme, I think maybe I just said this. My absolutes can be at the endpoints, or they can be within the interval. Okay, and the relative or local max and mins, those occur at the critical numbers of the function. Think about that, the critical numbers of the function. I don't know, maybe you're going, well, that's very excellent, but what is a critical number? Okay, well, let me show you what a critical number is. If I had a drum roll, we could go there. I do have one, rim shot, should put that on there. But anyway, so that's a critical number. No, that's not a critical number. As it turns out, critical numbers are the values of a function where the derivative of the function is equal to 0, or possibly is undefined. So we can have a critical number where the function is undefined. So if we're looking to find the critical numbers of, I just want to make sure I didn't leave space on the next page. If we're finding the critical numbers of x squared plus 5x plus 6, what we're looking for is the value where the function is equal, where the derivative of the function is equal to 0. So as I promised, we still have to take derivatives in this unit. And so we do the derivative, and the derivative of x squared plus 5x plus 6. Anybody? Yes, great. It's 2x plus 5. And so we want to know, when is 2x plus 5 equal to 0? Well, that's when x is equal to negative 5 halves. Okay, so negative 5 halves is a critical number for my function. Okay, which means it's a peak or it's a valley of the function. Okay, we know this is a parabola. Which way does this parabola open? It opens upward, right? Okay. You like that I pretend to hear you? So it's a critical number. It's the peak of the valley. It's the vertex, right? That's the low part. And the low part happens when x is equal to negative 5 halves. Okay, remember negative 5 halves? Remember what that this line right here is called? It's called the line of symmetry. A little Ferris Bueller thing. Anybody? Anybody? The line of symmetry. I don't know if I started talking softer. I should keep that deep, booming voice. Should have Morgan Freeman do these for me. But alas, we don't have him. There you are. I don't know what I was doing. Critical numbers. Find the derivative. Make it equal to 0. Solve the equation. So this goes back to Math 1 sort of stuff. This goes back to calculus stuff. So if we have a closed interval, and a closed interval means we have a definite beginning and a definite end. Okay? So we want to find the extrema on the closed interval. We want to find out whether we have, basically we're trying to find out the absolute max and the absolute min on a closed interval. So from some place to some place. So the first thing we do is we find the critical numbers. Next, we evaluate the function at the critical numbers. We also evaluate the function at the endpoints. And then we just have to make that decision. What's the biggest number? What's the smallest number? The smallest number, the least value, is my absolute minimum. The greatest value is my absolute maximum. Okay? So because we know that the absolute max and mins can happen at my peaks and valleys, or they could happen possibly at the endpoints. It's, I think, the same curve we started with before. All right, so let's try one of those. So my endpoints are negative 3 and 3. There's my function. So I first find the critical numbers, and first I find the derivative. Okay, 6x plus 2. I find out where the derivative is equal to 0. Okay, 6x equals 2. X equals 2 divided by 6, which I think is 1/3. Okay, and then we just jump to the place where we're going to evaluate the function at those critical numbers. We're going to find the f of negative 3. And the endpoints. We're going to find the f of 1/3, and we're going to find the f of positive 3. Okay? This is going to require some arithmetic. Negative 3 squared is 9. 3 times 9 is 27. 27 minus 6. Minus 6 more is like 27 minus 12, which is like 15. All right, I'm going to do the other easy end here. I'm still going to have 27 as my front end. I'm going to this time add 6 and then subtract 6 because 2 times 3 is 6. So I'm going to be left with here is 27. And I'm going to go with a third. And this one's going to be a little more difficult because it's a third. So a third square is a ninth. 3 times a ninth is 3/9, which is also known as 1/3. And then minus 2 times a third, which I think is 2/3. And then minus 6 more. So negative 1/3 minus 2/3 is negative a third. Minus 6 more, I think, is at negative 6 and 1/3, which is 18, negative 19/3. Check my arithmetic. Please be sure to tell me if I'm correct or incorrect. So we have to now decide which is the biggest number, which is the smallest number, and I believe that's my biggest number. So my absolute max occurs at 3,27. My absolute min occurs at 1/3, negative 19/3, which makes sense because we're looking at a parabola, right? And so this is the vertex of the parabola, and that's the low point of the parabola. It would seem reasonable that that would be the case. Okay? All right, so let's move forward. I think you could do this one, right? Why don't you try this one, and we'll save a more difficult one for a little later on. Okay, we'll do a more difficult one a little later, but this is just find the derivative, check the endpoint. So you're going to do the f of negative 3, the f of whatever, possibly I think there might be 2 critical numbers on this one, the f of that, whatever, and then the f of 3 and make your decision. Okay, you can do this. We'll check on it as we move forward. All right, and then, see this one? What are we going to have to use? Friend of the quotient rule. So because still, quotients don't go away. We still have functions that's divided by. So let's just crank through the derivative here, find the critical numbers, and go. So, ODI minus high DO all over. All right, so here we go. Critical numbers, I've got to do a little more work here. That's 6x squared plus 12x minus 3x squared plus 5. Make sure we don't lose that double negative thing. And so this thing turns into what, 9? Sorry, let's try that again. Over that. X plus 2 squared. This turns into 3x squared plus 12x plus 5. Am I right? Over x plus 2 squared. Okay, we know we're going to have an issue with this thing. Could potentially have a critical number when x is equal to -2. Okay, so that's a possibility, but we know we're going to have an asymptote there because we're not going to simplify that out. So that doesn't really count as an absolute max or min because it's undefined at that point. So we're not going to worry about the denominator. We're going to worry about when is 3x squared plus 12x plus 5 equal to 0. And that's probably where I would use the quadratic formula. I'm going to pause this. I'm going to get out the calculator so we're not wasting time on this. Am I not recording? God, I hope so. Oh, there we are. Good. Pausing. All right, I'm back. I know you didn't really even think I was gone, but I am back. So we're just going to use the quadratic formula program that we popped into the calculators to get this to work, I think. He says, does it work? Why is it not working? That was delightful. Good use of technology. Come on now. Enter. Hit enter. What's going on with you? All right, pause it again. Oh, wait. No, not pausing again. You just want to work for me. Okay, so we're doing that. What were the numbers? 3, 12, 5. And so there's my roots, -0.4724, so -0.47. And the other piece, where am I going back to? -0.47, 3.52. So I get x equals -0.47. I should have another number after that, and x equals the -3.52. See if I can see those. 3.527472. That. Good Lord. Some technical difficulties. That was a 7, right? And so then we're just going to find, and this is sort of the monkey work part of things, the f of -1, the f of -3.527, the f of -0.472, that is, and the f of 4, and make our decision. Biggest number is the minimum, smallest number is the maximum. I would probably, if I had a calculator, I'd just go with that, put the y equals and do the y1 of whatever and go there. So I think you can do the monkey work portion of things. I know you could have done the derivative portion of things, but just reminding you the quotient rule. All right, so now sines and cosines, those are the next ones. Remember, those aren't going away either. So f primed, derivative of sine is cosine. Derivative of cosine is negative sine, so we have negative sine, so it's plus sine. Okay. I need to find out my critical number, so I need to find out when the cosine of x plus the sine of x is equal to 0. And notice I don't just put that equals 0 because it makes it like a run-on sentence. The derivative is not always equal to 0. We're looking for the specific case where it is. So that's going to be when the cosine of x is equal to the negative sine of x. And I don't have my trig card in front of me, but that is going to be some multiples of pi over 4. I don't know which ones it is, whether they're opposite signs, so the cosine and the sine, and just jump up here, all instinct calculus. So it's going to be in the third quadrant where this is positive. Let's see, in here, tangent. So these in here, they both have the same signage in here. So it's going to be in these two quadrants here. So it's going to be some multiple of pi over 4. So that's when x is something pi over 4. That one, it's going to be, what? I should probably just pause and grab my trig card. That would make more sense. So pi over 4, and so that's 3 pi over 4, right? And then it's going to be again at 7 pi over 4. Check that, okay? So derivatives, use the trig card, and then so again, we're just going to know the f of 0, and we go back to the original function, the f of 3 pi over 4, the f of 7 pi over 4, it's 7 pi over 4. I'm trying to get close to the 2-minute mark, or 15-minute mark, I know that. So we just check those answers and see what's going on. Biggest number's the max, smallest number's the min. That's how it works every single time. All right, so there's that. Okay, that's the work you're going to do tomorrow. So let's just stop there. And I think that's about it. I think that should do it. Okay, it's the extreme value theorem. There you have it. Where am I at? 1541. So sorry. Went a little over, but what's 44 seconds amongst all of us? We'll see you. We'll see you tomorrow. Thanks for watching. Hope you learned something. If you have questions, you let me know. Thanks.